This lecture is about logarithmic differentiation. Now you might be thinking, well, didn't we just learn the derivative of log functions? And yes, we did. This is a different strategy. So derivatives of log functions, we already have a log function and then we try to do the derivative of that log function. And for logarithmic differentiation, we actually introduce the log ourselves. And it's used for complicated like products and quotients like this, or it's also used for when I have basically a function of x raised to a power that also has an x in it. And so this is a very useful tool. So we have some steps here. So step one here is to take the natural log of both sides. Now I really want to use natural log. I don't want to use log because when I do the derivative of natural log, I don't have to tack on that dividing by the log of the base. So I definitely want to use the natural log. So let's do that. So we're going to take the natural log of both sides. So on this side, we're going to have the natural log of y equals the natural log of all of this stuff, x squared times, I'm going to write this x squared plus 1 as x squared plus 1 to the 1/2. And then down here we have 3x plus 4 to the 3rd. Okay, so I have the natural log of all of this stuff. So then our next step is to use the properties of a log to simplify it. So basically we're going to expand them. So there's a product rule that says if I have things multiplied together, then I can write them as the natural log of this plus the natural log of this because these two things are multiplied together. And if I'm dividing, then I can subtract. It would be the natural log of all of this minus the natural log of this. So that's what we're going to do. We're going to expand it. So we're going to have the natural log of y equals, let's see, the natural log of x squared plus the natural log of x squared plus 1 to the 1/2. And then this is in the denominator, so we're subtracting it, minus the natural log of 3x plus 4 cubed. All right, so now I have it nice and expanded. And so I have one more rule that'll actually help me a little bit, and that is the power rule for log functions, meaning I like logs in the first place because I can pull all the powers down in the front. So the left side doesn't change, it's still ln y, and then this will be 2 ln x. I'm not doing the derivative of at all right now. I'm just breaking apart my function into little bitty pieces. So I have, and then 1/2 ln of x squared plus 1, and then minus, the 3 can come down in front here, 3 ln of 3x plus 4. Now I can apply the derivative of both sides. Now when I do that, I have natural log of y over here, so I'm going to have to use implicit differentiation over here. So when I do the derivative of ln y, I get 1 over y dy dx. Right, so now the rest, these are all in x, so we can just do the derivative. So 2 times natural log of x, so the derivative of natural log of x is 1 over x, so that's 2 over x. Then this is going to be plus, I'm just going to put the half out front here, times, right, so it's 1 over this, x squared plus 1, times the derivative of this, the 2x goes on top. Then I have minus 3, and then I know 3x minus plus 4 will go on the bottom, and then I have to multiply by the derivative of the inside here, which is 3. Right, so now I have dy dx. I still have the 1 over y here. So I'm going to actually multiply both of my sides by y, right? I just want the derivative. So I'm going to multiply this side by y and this side by y. So I have y times all of this stuff. I have 2 over x plus a half times, I'll just write it like this, 2x over x squared plus 1. I can actually simplify this a little bit more. I can cancel out my 2's here if I want to. And then minus 3 times 3 is 9 on top over 3x plus 4. All right, now we only want this in terms of x, so all we have to do now, though, we have this y in here, but we already know what y is. Y is this thing. So we just replace y with that thing. So let's see, I'll just copy it down here. So y is, just rewriting what's up above, I'm not doing anything to it, x squared times the square root of x squared plus 1 over 3x plus 4 cubed, and then this is times this stuff. So 2 over x plus then I just have x over x squared plus 1 because my 2's canceled out there. I canceled out the x instead, but it was that way. And then I minus 9 over 3x plus 4, and there is my derivative. Okay? So when I have a bunch of things multiplied and they all have a bunch of weird powers on them, this is kind of a nice way to make it a little simpler. Now the derivative doesn't look simpler, but it's actually easier to take the derivative of it this way. Because if I was going to do this one, right, I'd need a quotient rule first. When I did the derivative of the top, I would need both the product and chain rules. And when I did the derivative of the bottom, I'd also need a chain rule. So this kind of uncomplicates it, although visually complicating the derivative at the same time. So, but it's a little bit easier to do. All right, so let's do another one of those. Okay, so this time I have a bunch of multiplication, and I'm going to use logarithmic to make it a little bit easier. So I'm going to take the natural log of both sides. So I have ln y equals the natural log of all of this. So when I do this, it's not pieces, it's all of it, all at once. I take the natural log of the whole side. All right, so now I have a bunch of multiplications, so I can break this side up. I'm just going to leave ln 1 for a second. This is the natural log of, I'm going to change the square root to x to the 1/2. And then this is plus the natural log of e to the x squared plus the natural log of x squared plus 1 to the 10th. All right, so ln y is still over here. All right, I'm going to pull down my exponents here. So that means I have 1/2 times the natural log of x. And then this is going to be x squared natural log of e. The natural log of e, actually these two things, right, they do undo each other. When I have the natural log of e to the x, it's just the x. So in this case, if I pull down the x squared, I've got x squared ln e, and ln e is actually just 1. So this part just simplified to x squared. And then this, I'm going to pull down the 10 in front, 10 ln of x squared plus 1. All right, this is still really y, just in a different form. Now I'm ready to do my derivative. So on this side, it's always going to end up being the derivative of y, which is, or the natural log, which is 1 over the y, but then it's y, so I tack on dy dx is equal to, all right, so this is just going to be 1/2 times the derivative of the natural log of x, which is 1 over x, so I'll just put the x down here with the 2, and the derivative of x squared is just 2x, and then here I'm going to have 10 on top. I'm going to have the x squared plus 1 on the bottom, right? It's 1 over, then times the derivative of the bottom, which is 2x. All right, so cleaning it up a little bit. So I'm going to multiply it over my y here and clean it up at the same time just to save myself from writing it a bunch of times. So this will be y times all of this, so 1 over 2x plus 2x. And then I'm going to combine these two and call them 20x over x squared plus 1. And then my last step is to get rid of this y, and y was just this thing up here, so I just write it in place. So my derivative is, so the square root of x, e to the x squared times x squared plus 1 to the 10th. That's all my original function. I changed nothing about it. They're all supposed to be on the same line there. Kind of looks like my e's floating up in the air, but it's all together. And then, so that is y, and then I just write the rest of the stuff, 1 over 2x plus 2x plus 20x over x squared plus 1. And that's it. Okay, so we've done a couple of that type. So now let's look at this one. Okay, so this one really so what I notice about this, and this is where logarithmic differentiation comes in really handy, is that I really have a function of x to a function of x, right? So if I have variables in the base and the exponent, then I really can use logarithmic differentiation to help me out, okay? So I'm going to change this to y over here equals x to the cosine of x. F of x and y are just interchangeable. And then I'll do the natural log of both sides, so I get ln y equals natural log of x to the cosine of x. All right, so the derivative, actually, no, don't let me do the derivative yet. I can pull down this exponent, so this will be the cosine of x times the natural log of x equals ln y. So again, derivative of ln y is 1 over y times the derivative, because it's not x, because we were doing dy dx, so that when the variables don't match, we tack on d, the name of the variable, over d, the variable, right, equals. Okay, so now this time, I actually have a product. So I'm going to use the product of cosine times natural log. These are both functions of x. So I'll do the derivative of cosine first, which is negative sine times ln x. And then I have plus, then cosine of x times the derivative of natural log, which is 1 over x. So I'll just write it like this. All right, so now I need to multiply across my y. So my dy dx equals y times, I don't like leading with a negative sign, so I'm just going to write them in a backward order. So this is then minus sine of x, ln x. The order really doesn't matter. It's just I tend to lose my minus signs if they're in the front, so this is my accommodation. And then now I know y is this, so it's a little easier to write y. I don't have to write a big complicated function here, but so my derivative now in terms of x is, my y now becomes x cosine of x times cosine of x over x minus sine of x natural log of x. Okay. All right, so let's do one more of those. So I have y equals x ln x. Again, my base has an x in it, and so does my power. So I'm going to take the natural log of both sides. The natural log of y equals the natural log of x to the ln x. Now I'm showing every step. Like if you can do a couple steps at a time, that's fine. I'm just trying not to confuse anyone. All right, so I'm going to pull down my exponent in front. So I get natural log of x, natural log of x. So I'm going to just, I could use the product rule here, but the chain rule will actually be faster if I write this as the natural log of x squared. And I have ln y equals. All right, so now I have my derivative of ln y is the same every time, 1 over y, dy dx equals, and now I'm going to use my chain rule here, so the power goes first, so 2 natural log of x, now to the first, which we won't write, times 1 over x. Then I'm going to, as my final step, my dy dx, I'm going to multiply over here y times, and I'm just going to write it like 2 ln x over x, just for neatness. And then I'm going to replace my y. So my y goes back to x ln x. So I have x ln x times 2 ln x over x. And this is the derivative. Okay. So again, we use logarithmic differentiation. It's extremely helpful here, right, when I have basically a power and a base that both are functions of the same variable. And so then we can, it allows us to pull our power down and then take the derivative of it. And then we can also use it on very complicated multiplication and quotient type derivatives. All right.